Hello guys, welcome back to Maison African Motives, still on our industrial electronics N4 revisions, working on power supplies. This part is on the rectification part, whereby we're given, that's question 1, question 4.1. This is actually from November 2022 exam, whereby we shall be focusing on this circuit, which is a capacitor filter in this case that we are given. That is a full wave rectifier circuit. Here, as you can see, I've got a bridge circuit. So the question is, answer question 4.1 with regard to the circuit in fig 3. So whatever that you're going to have is going to be taken from this fig that we are seeing here. So as we can see, we've got the input here, which is from the sine wave. Then as we know that enters the rectifier for rectification, the input, then V out from our transformer to the rectifier, which is a bridge. In this case, we are referring to a full wave bridge rectifier. In this case, we're talking about a full wave bridge rectifier. Because of the capacitor here that we are having, we are going to consider this as a capacitor filter. All right. So the question is, yes, we are dealing with the rectifier, but as we are dealing with our calculations, we are going to consider this as a capacitor filter, just like this part here, whereby we are given a full wave shunt capacitor filter with a bridge, in this case a capacitor, followed with a load resistor in this case. All right, so that is the condition that we are working with. So we are given the first part of the question. In this case, it was the circuit represents a wave or rectifier. So this is a full wave since we've got a bridge there. All right. Draw the output waveform from 0 to 540 degrees. All right, so in this case, we were going to have your output from 0 to 540 degrees. In this case, like this one, where we are given this format. So just gonna explain from this part that we are given. All right, whereby we are having from 0, then this is half of the time. Here we're talking about the cycle. All right, the T here, we have completed 360 degrees. So here we are at 180 degrees, which is half of the cycle at 360 degrees. Then at 540 degrees, meaning say we are supposed to end here at 540 degrees, all right, up to the capacitor discharging. So showing the points of cut off, cut in point, the cut out point, and also the capacitor charging. This was the part that we are supposed to be working with. All right, my major part here is on the calculations, guys. My major part of this question is here. You're supposed to be very, very careful here. We are asked to calculate the output DC. In this case, we're talking about the output DC. That is at the end here. We are going to refer to output DC. So like I said, this is a rectifier, which is fine. It's a full wave rectifier. But it's a full wave rectifier shunt capacitor filter. In this case, we are considering a capacitor filter. So the calculations that you're supposed to take, or the formulas that you're supposed to be working with here, are supposed to be taken from a capacitor shunt. I'm just going to rephrase from your syllabus. You remember what we are required to understand about our capacitor filter. In this case, a table formula for a simple capacitor filter for both half wave rectifiers and full wave rectifiers given are given below. So this is what you're going to be considering for a full wave, because here we are considering for a what? A full wave rectifier circuit. All right. So we're asked to calculate that is the output, which is our VDC this case. So if we are to check here, our VDC is given. We are going to consider this part for a full wave rectifier here. That is our VDC is going to be taken from this formula, which is VM into VM minus IDC over 4 FC in this case. That is the one that you're gonna consider, or we can have our, we've got the VR P, which is the peak that you're going to consider, but in this case, we do not have these values. So we are going to consider this formula here for VDC under the full wave, this one, all right? So let us get back to the formula. I'm going to explain with what we are given on our diagram here. So this we are given, that's 4.13. So 4.13, we are going to have the output voltage, which is our VDC in this case, which is given by the formula. As we saw, it's VM minus IDC, which is the DC current that we are going to have at the output over 4FC, which is the frequency, times the capacitance value. Remember, we've got a capacitor in this case here of 10 microfarads in this case. All right, so considering our VM, this is the voltage that is entering, which is the one that is at the rectifier of 15 volts in this case. We're going to take this VD, which is actually our VDC in this case. That is the maximum value that we can obtain of 15 volts. That is from our AC, from the AC that we are having at the input. All right, but this is the input to the rectifier, but it's an output from a step down that happened from this transformer. All right, so we are going to consider this as our VM. All right, so that is your VM in this case on this when you're dealing with a shunt capacitor, which is a filter in this case. We are going to see when it's a rectifier on its own, when you're not having a capacitor circuit, the formulas, they are going to be different. So that's why I am emphasizing on this part. You're supposed to be careful on your formulas. All right, so our VM there is supposed to be 15 minus, this is the output current that we have at the load in this case. So at the load here, we have got the current that is going to flow through the load of 10 milliamps. So we are going to obtain, we are going to have there 10 times 10 to the exponent of minus 3 over 4 times the frequency. Remember, the frequency of the circuit is taken at what? At 50 hertz in this case. This is our frequency at 50 hertz. So we are going to use 50. Then the capacitance value in this case, our capacitance value is 10 microfarad. All right, that is the value of the capacitor, which is 10 microfarad. So that's 10 times 10 to the exponent of -6. All right, so that's it. We are going to obtain the voltage, which is our DC voltage, which is at the output in this case, which was going to be 10 volts in this case. All right, so that's it. It's a matter of knowing the type of circuit and also the formulas. Each and every type of circuit is going to be followed by its own formulas. All right, then we're asked to calculate, in this case here, we're asked to calculate the output ripple voltage. All right, the output ripple voltage in this case. If you have to take note, again, on our formulas, the output ripple voltage is the one that is given by the RMS. This is a VRMS for the ripple voltage, RMS, at the output in this case. All right, so if we are to check on our formulas again, if you are to check for a full wave, if we are to check the formula for VRMS in this case, we are going to consider all right, we've got this part here of our VRMS, which is equivalent to IDC, which is the output current in this case that we have over 4 square root of 3 FC. So we are going to consider, remember, we are dealing with what? With a full wave rectifier in this case. All right, so that's the formula that was going to be the best to apply in this case. So this is going to be given as we saw, it's IDC, which is the output current, 4 square root of 3 times the frequency times the capacitance. All right, of which we have got this current here. We talked about this current before. If you take note here, we substitute this current. It was 10 times 10 to the exponent of -3. So that's 10 times 10 to the exponent of -3 over 4 square root of 3 times the frequency. Already we substitute our frequency before, it was 50. The value of the capacitance, remember, it was 10 micro, which is 10 times 10 to the exponent of -6. So this one, just a substitute. The only part that we do not have, that we needed, was the current there. Otherwise, everything is going to be the same. All right, so simplifying this, we are going to obtain something like 2,887. So that's 2,887 volts. All right, that's we are having the output ripple voltage in this case. And we asked to calculate the load resistance again. The load resistance, as you can see at the load here, we've got in this case, remember, we calculated the voltage at the output, which is our VDC, and here we have got IDC. So meaning, so you can simply use these two to calculate the value of the load resistance. So that's simply voltage over current. All right, so that's 4.15. So the load resistance is simply going to be the output voltage of the current in the at the output in this case, of which we've got we calculated the voltage, our VDC. In this case, we got 10 volts here. So we are going to use that 10 volts. All right, so this is going to be 10 over the current that is flowing at the output. At the output, there's a current of 10 milliamps. So that is, we are going to divide by 10 milliamps. All right, so that's it. We have got the resistance across the load, which was going to give us 1000 ohms in this case, of which 1000 ohms is same as 1 kilo ohm. Remember, that's 1000, that's a kilo in this case. Okay, so that was the question. And 4.2, it's a direct question that we are given. In this case, we are given name 2 types of transformers in this case. Remember, when you're dealing with transformers, we can be talking of a step down, whether it's a step down or it's a step up, right? So you can have it as a step down transformer, or you can have it as a step up transformer. We can have it as a center tap transformer. There are so many types, guys. You can have it as a center tap. We can have it as a multiple winding or isolation. You can have it as a multiple winding transformer. We can have it as an isolation transformer. So many types that we can actually list. If you have got others, let us know on the comment section so that we can help others also in our revisions towards our exams. All right, so that was it. 4.3, what is rectification? All right, remember the part of rectification is a conversion part that is happening between AC and DC in this case. So we can simply say this is a process. Okay, it is the process. So this you can label as the process of converting. So we're gonna be converting in this case an alternating voltage in this case, an alternating voltage. So we are going to call an alternating voltage to a unidirectional voltage in this case. All right, so we're gonna convert this to a unidirectional voltage, which is a DC that we are going to have at the end. All right, that's how we are simply talking about the part of our power supplies. You just need to revise as much questions as you can. Just work with more questions. Each and every part you need to know its properties. So that is the part of our power supplies. You need to know each and every circuit. Is it a full wave? Is it a half wave? You're talking about filter circuits. Know each and every circuit and its application. You'll be able to answer these typical questions that we are having.